Hello, welcome back. So in this video, we will do activity 7.4. So we have question number 1, and this is saying that we have x1 to xn random variable and s is defined as a1 times x1 plus a2 times x2 till an times xn. And choose the correct options from the following. So we have to choose the correct option from the following, and so it is about expectation and variance of this S. So we know that expectation and variance of this. So there is no other information is given here. It is given that let x1, x2 to xn be random variables such that s equal to this. So no other information about independence or about IID is given for these x1, x2 to xn. So we know that for expectation of, sorry, not S, it is for S. So we know that expectation of S we can write as this a1 x1 up to an xn, and here so from the properties of expectation we can write it as expectation of a1 x1 uh, till expectation of an xn. And we know that, so here we don't need to have x1 to xn as independent, because without any no matter whether x1 to xn are independent or dependent, we can write them as this in this form. Now we can take this constant common, and then this is also from the property of expectation. So when we will take this constant out, it will become a1 times even of e of x1, and similarly for each of these xi's, an times expectation of xn. So this will become expectation of s, and that is the second option, I guess. And the variance of this we cannot write anyway, because variance of s, which is equal to variance of a1 times x1 plus a2 times x2 till an times xn. So this, to break this, to put this variance inside, or to write this as the sum of the variance of individual xi's, we need the condition which is x1, x2 to xn are independent. So since here there is no information is given about the independence, we cannot write like that. So this will be just this. So we cannot say this. So let me write this like that. So it is not equal to a1 squared times variance of x1 plus an squared times variance of xn. This is not true. Why? Because x1, x2, xn are not independent. Okay, so now let's discuss question number 2. So question number 2 says that we have n equals to 50 IID samples. IID samples. So whenever it is written like that, we can write it as x1, x2 to xn, and where xn n is 50, so till x50. And using weak law of large number, find the correct options. So we know what is weak law of large number. So I will write it as some. So this is very important. So this is probability of. So it basically comes from Chebyshev's inequality. So probability of x bar minus mu greater than epsilon, that will be less or equal sigma square by n times epsilon square. So here few things are really important to understand. So this sigma here is indicating the this mu here indicating the mean of x, not the x bar. So this is important thing to note. This mu is expectation of x, right? And what is x here? So we have this IID, right? X1, x2, x50, they are IID. So I can write it as these x1, x2, x50 are IID x, right? So this is what the expectation of x. And this sigma square here, this is also coming from variance of x. So these are the important things. So this is not about the variance of x bar and expectation of x bar. So okay, it might look like that. Okay, now it is fine. So this mu is expectation of x, and the sigma square is variance of x. Now n is same. We have n equals to 50 here. So we need so this is a weak law of large number, which says that which tells the bound about the difference of actual mean and sample mean. So now let's go back to our question. And our question is saying uh, for Bernoulli 0.6, let's say. So the first option has Bernoulli 0.6. So this is my x. Right? This x is Bernoulli 0.6 samples with probability more than 0.52. Sample mean lies between this. So it is saying that my sample mean lies in this range. Which range? 0.41 and 0.31. So this is what we need to verify whether this is true or not, which means the sample mean lies in this range with the probability more than, so it is true with probability more than 0.5, 0.52. So this we have to verify. So how do we include this vehicle of large number in this? So we have to write some our x bar in terms of this, right? We need to write our x bar from the vehicle of large number expression in terms of this. So to write this, let's a little bit simplify vehicle of large number expression, which we can write as x bar. So I'm removing this mod of I'm removing this mod, and I can write this as okay. So before that, let's write it as 1 minus p of x bar minus mu less or equal epsilon less or equal sigma square by n epsilon square. So it is just like something greater than, so we have this property, that property of x greater than alpha can be written as 1 minus probability of x less or greater or equal, sorry, less or equal alpha. Right, so I'm using this property here. And now I can simplify more. I can write this as p of x bar minus mu less or equal epsilon greater or equal. I'm sending this term to the right hand side, and this left hand side term to the uh, this right hand side to the left hand side. So that will become 1 minus sigma square by n epsilon square. Now our expression looks little bit simpler. And now let's open this mod. So now our expression will become x bar less or equal epsilon by mu, sorry, epsilon plus mu, and greater or equal, this will become mu minus epsilon. You can verify this, and then greater or equal 1 minus sigma square by n epsilon square. Now we have this expression, and you notice one thing here. My this thing which is inside the probability, this thing is equal to so it's kind of similar to this expression, and which is what we wanted to do. So once it is similar to this expression, what we want is we want this epsilon plus sigma to be equal to 0.41 and epsilon plus mu to be equal to 0.41 and mu minus epsilon to be equal to 0.39. That is what we want. So if we can achieve this, so using any one of these two expression, either sigma plus mu or mu minus sigma, I can find the value of sigma because mu is already given to us. And what is the mu? Mu is simply just this value, 0.6. So once we get the mu, we get the sigma, and we know all the values to the right hand side. Like we know the value of variance sigma square, we know the value of n, and after getting the value of sigma, we can put that here, and sorry, the epsilon. So I'm calling it sigma. So sorry, this is not sigma, this is epsilon. So after getting the value of epsilon from here, we can put that value of epsilon in this, and all other values are known, and we will get our upper bound, which we want to be 0.52. If it is coming out as 0.52, then first option will be correct. So that is what we are trying to verify. Okay, so now I have written this again. I have removed other things, and now we have this expression which is here. So what we want is we want mu plus sigma to be equal to, sorry, mu plus epsilon. I'm calling it again and again sigma. So pardon me for that. This is epsilon. So mu plus epsilon should be 0.41, and mu minus epsilon should be equal to 0.39. So I can solve any one of it to get the value of epsilon. So let's say I'm solving this, and to get this, it is 0.41 minus 0.6. But from here, if we get the value of epsilon, it should also be equal to the value. It should be equal to the value which we are getting from here. So here it is 0.39 minus. So sorry, it will go here. So this is minus and plus 0.6. So to verify this, uh, let me calculate these values. So 0.41 minus 0.6 will come out as, here epsilon will come out as 0.19, negative of 0.19, and here epsilon will come out as uh, so anyway, so whatever it will come, it will be positive, right? So that is not uh, so that's violating our condition, which is like same value, same constant cannot take two values. So that is the first option cannot be true, because we cannot apply weak law of large number here, since this epsilon is coming different. So certainly it is not going to fall in this range. So this is, we should get same epsilon for both the cases. So first option is not correct, and let's go to the second option, and we will discuss about one correct option, and then other option can be verified from a similar manner. Okay, so we have, okay, so we have, let's say, let's go to the second option, where we have Bernoulli 0.4. So this time we have our x as Bernoulli 0.4, and in this we need to find the probability that my x bar uh, is in the range of 0.5 to 0.3 to 0.5. So that is the uh, so we need to use this weak law of large number to verify whether this is true or not. So to verify, again we have our expression that we got from the previous option. We will write that here again directly, which was this less or equal mu plus epsilon greater or equal mu minus epsilon, and that was greater or equal 1 minus sigma square by n epsilon square. So here again what we want is, we want this sigma plus epsilon to be equal to 0.5 and sigma minus epsilon to be equal to 0.3. So if we look at here, our mu is 0.4, so sigma is coming out at 0.1 here, and from here our, sorry, epsilon is coming out as 0.1 here, and from here epsilon is coming out as 0.1. So you see, both in the both cases 0.1 is coming out as same. So now we can apply, that means we are good to go with our weak law of large number. That means we got the value of epsilon, which is 0.1, and now we have to put this here, and we need to get 0.52, which is given in the option. So we should get 0.52 after putting the value of epsilon, which is 0.1. So let's see whether we can get or not. So this epsilon sigma square is 0.24, because sigma square will be the variance of Bernoulli x, which is Bernoulli 0.4, So the variance is p into 1 minus p, which is going to, and here p is 0.4. So our sigma square will be 0.24, and our n is 50, and then this is 0.1 times 0.1 will become 0.01. So by solving this, we will get 0.52. Hence, the second option is correct. Similarly, you can find out you can verify whether other options are correct or not. You just have to follow the same process, and you have to verify whether you are getting, whether you are getting this sigma same from both cases or not. It should be same from both, because the same constant cannot, or the same variable cannot take the two different values here. So here our epsilon will take at the same time it cannot take two different values. Okay, so this was the question number 2. Now we'll move to the question number 3. Okay, I'm keeping this weak of large number expression as here because we are again going to use that. So now we are we are solving question number 3, in which it is saying that our n is given as 100. So a random sample size of 100 is collected from a population with the standard deviation of 25. So this standard deviation is given, which is 25. So here you notice that this is not the sample standard deviation. It is a standard deviation. Standard deviation is related to the population. So here we will not call it as standard deviation of sample. It is the standard deviation of population. And now what we have to find is find the lower bound on the probability that sample mean will be at most 5 units. So we have to find that the sample mean x bar will be at most 5 units away from the actual mean. So let's call actual mean as mu. Mu is our actual mean. And so let's try to figure out what the question is asking. So the question is asking that we have so this is the number line, and let's say here I have my actual mean mu, and so uh, 5 units away from the actual mean. So what is the interval which is 5 units away from the actual mean? So I can go here in this direction, 5 units away from the actual mean. Let's say this is the 5 units distance, and that will become mu plus 5, right? And this 5 units away can be from it will be in both directions. It can be in both directions. So I can go here also, same 5 units away, and that will be mu minus 5, right? So this interval here is 5 units away from mean. So this is the 5 units away from mean interval. So the question is asking now is find a lower bound on the probability that the sample mean will lie in this interval, right? That means sample mean uh, will be at most 5 units away from the actual mean. At most means it can be only this much away. It cannot be more than that. So it can be less also, but it cannot be more than this. Means my sample mean my sample mean cannot be here, and similarly my sample mean cannot be here. So we need to find the probability that my sample mean is in this interval. So to find this, again we have to use the weak law of large number, because it is asking to use the weak law of large number. And so again the same thing. So what is the rate? So what is the interval for my x bar, which is the sample mean? It is mu plus 5 and less greater or equal mu minus 5, right? This is the interval, and we have seen how to convert this expression of weak law of large number into this expression, right? So we will write that expression again to make the same thing simpler. I will remove this from here. So what we have is probability of x bar less or equal mu plus epsilon greater or equal mu minus epsilon, and that will be greater or equal 1 minus sigma square by n epsilon square. Right? That is the expression from the weak law of large number that we have. Now we have to put the value. So we need to find the probability of this thing, right? Probability of this, which is x bar less or equal mu plus 5 greater or equal mu minus 5. So here you see we need to find the lower bound. So here so this will be 1 minus sigma square n times, and epsilon is what? So epsilon is 5 here. So you see this is my epsilon, this is my epsilon. If you compare these two expressions, you will find that epsilon is 5. So you will put 25 here, epsilon square is 25. Now we have all other information also given, because sigma is 25, then sigma square is 625. So it is greater or equal 1 minus 625, and n is also given, which is 100 times 25. So after solving this, we will get 0.75. So that is the question number 3. So that is all about uh, activity 7.4. In the next video, we will discuss the another activity of week 7. Thank you so much.